Welcome to the lecture number 8 of the course Discrete-time Markov chains and Poisson processes. So, recall that in the last couple of lectures we have talked about stochastic process, then Markov chain, and then we have seen some properties of Markov chain, and one of them was Chapman-Kolmogorov equations. And then in the last lecture we have seen how we can use Chapman-Kolmogorov equations to find out probabilities in different scenarios. Of course, in those cases we have to first write our problem in terms of Markov chain's term, and then using the Chapman-Kolmogorov equations we can find out what are the probabilities of different events to occur. Okay? Now, today we are going to discuss with some important concept of Markov chain called accessibility and communication. So, we will discuss those issues today, we will address those things today, and we will see couple of examples how to illustrate this accessibility and communication concept. So, what is accessibility? Accessibility is a very standard term that accessible basically mean that I can go from one place to another place. So, maybe that Delhi is accessible from Noida, that basically mean that I can go from Noida to Delhi, or Delhi is accessible from Kolkata, that basically mean that I can access Delhi from Kolkata, and similarly Kolkata is accessible from Guwahati, means that I can go to Kolkata from Guwahati. Okay? So, this is basically the essence of accessibility. It is true in case of Markov chain also. So, let us see the definition first, then we will discuss other things. Okay. So, definition tells that state J is said to be accessible from I. So, suppose I have a state I have a state J. Now, state J is said to be accessible from I if there exists some n greater than equals to 0, if there exists some n greater than equals to 0 such that Pijn is strictly greater than 0. Okay? Pijn strictly greater than 0, just recall that what was Pijn? Pijn was probability that xn equals to j given x naught equals to I. Okay? So, I can go from I, starting from I can go to the state j in n steps. That is basically the probability, that is basically the Pijn, and the definition says that that quantity is strictly greater than 0. If this quantity is strictly greater than 0, then we say that I can go from I to j. Okay? And so, j is accessible from I under this scenario. Note that I have given one particular thing here. Just recall that we have defined Pijn for n equals to 1, 2, so on so forth. Pij 0 was not defined earlier. So, but because I am taking n equals to 0 also here, n equals to 0 is included here. So, I am just defining what we mean by Pij 0. So, Pij 0 we have defined at delta ij, which basically mean that it is 1 if I equals to j and it is 0 otherwise. So, that means I mean the intuition is that I can go from I to I in 0 step always, because I am already in I. So, of course, I can, if I do not take any more step, I will be in I. So, that is why this quantity is 1 and Pij 0 is 0 for all j not equals to I. Okay? That is basically the convention that we are going to take in this case. So, accessibility mean that I have some n, note that some n, if I get one n which is greater than equals to 0, such that Pijn is strictly greater than 0, Pijn is strictly greater than 0, I am done. I can tell that j is accessible from I. I can tell that j is accessible from I in this case. One notation now onwards we are going to use is that Pi dot is same as p of r dot given x naught equals to 0. So, instead of writing this x naught equals to 0 here, I will just write I here, that basically mean that given x naught equals to 0, I am trying to find out the probability. Just for example, that instead of writing that p x n equals to j given x naught equals to I, just we have written here, I will now onwards I will write this probability as pi. That means starting from I will go to j in n step. I will be in the state j after n step. Okay. So, this particular notation I am going to use now onwards. This is nothing but to shorten the notation. Instead of writing this x given x naught equals to 0, I will just write I here. That basically mean that under the condition x naught equals to I am trying to see the probability of some event. I am trying to see the probability of some event. In this case, in this example, I am trying to find out the probability of x n equals to j given x naught equals to I, that I will write pi x n equals to j. Okay. So, with that notation and with this definition of accessibility, let us proceed. Note that this definition tells that, well, p I j n is strictly greater than 0. So, what does this mean? Does this mean that I can go from I to j, and this actually given by next theorem. So, this theorem basically gives us 3 conditions, and these 3 conditions are equivalent. Okay? This theorem gives us 3 conditions, and theorem tells that these 3 conditions are equivalent. So, let us see what are the conditions. So, for distinct state I and j, so here I am assuming that I and j are not same. I and j are 2 different states. So, the followings are equivalent, the following statements are equivalent. So, what are the statements? First says that j is accessible from I. Second statement says that probability, that conditional probability that starting from I will be ever in j, that probability is strictly greater than 0. So, starting conditioning on the starting from I, the conditional probability that ever be in j will be strictly greater than 0. And the third condition tells that there exists some states I naught has to be I and I n has to be j, and in between I have I 1 I 2 to I n minus 1. In between this n minus state can be anything. So, I have some state I naught, I 1, I 2, I n minus 1 and I n, such that if I take the product of these probabilities are that from I go to I 1, then from I 1 to I 2, then I 2 to I 3, so on so forth. Finally, I n minus 1 to I n, and I n is j, so I n minus 1 to j. If I take the product of these probabilities, that has to be strictly greater than 0. For some states I naught to I n, where I naught has to be I n has to be j, and in between state can be anything, and for some n greater than equals to 0. Okay. So, these 3 statements are equivalent if I is not equals to j. If the state I and state j are not same, then they are equivalent. So, let us now understand each of them separately and try to prove them. So, first j is accessible from I, we know by definition, that means there exists a n greater than equals to 0, such that p I j n is strictly greater than 0, that is basically the definition. Okay. Now, what does this physical meaning of the second statement? The second statement says that because 1 and 2 are equivalent, the second statement says that if j is accessible from I, that means starting from the state I can go to state j. I can go to state j ever be in state j, that means in some step I will be in state j. Okay. Ever be in state j, that basically mean that some stage I will be in state j. So, it says that, well, if there exists a n greater than equals to 0, such that p I j n is strictly greater than 0, then the conditional probability that ever be in state j given I am starting from I is strictly greater than 0. And notice the starting from I, that is equivalent to write that x naught equals to 0. Okay, sorry, x naught equals to I, that is basically writing same as x naught equals to I. Okay. So, this is basically equivalently I can tell that probability that ever ever be in J given x naught equals to I, that is strictly greater than 0. The starting from I, that basically means x naught equals to I. And what this third condition tells that? Third condition basically tells that, well, I have I here, I have j here. If j is accessible from I, if j is accessible from I, that means I have some state in between, I have some state in between such that I have a path through these states to grow from I to j. I have a path through these states to go from I to j. Okay? And there is a path, that means that there is a positive probability that I can go through this road from I to j. I can go through this path from I to j, that has positive probability, that means there is a path, there is a path. Okay? So, let us try to now prove this thing. So, we discuss the physical meaning of this thing, and now let us prove this thing. So, proof, first what I am going to do is that I am trying to prove the equivalence between the statement 1 and statement 2. That means, j is accessible from I and probability ever be in j given starting from I is strictly greater than 0. First, we will try to prove the equivalence of these two statements. So, the proof goes like this. See, we know that because j is accessible from I, so there exists some n for which p I j n is greater than 0. So, I take that particular n here. Okay, for which n p I j n is strictly greater than 0, that particular n I have taken here. So, I have written p I j n, and that is by definition starting from I going to j in n step. Okay, I will be in j in n step starting from I, this is basically this probability. Now, now you just consider this probability also, this probability again starting from I, that any of the x n equals to j, any of the x n equals to j, because I am taking union, and union basically mean that collection of everything. So, any of x n equals to j. So, clearly this a particular n is a special case of any of the n, that means that x n equals to j is basically a subset of union of x n equals to j, n runs from 0 to infinity. Okay? It is a subset of this quantity, because here all the n's are included, here I have a particular n. Okay? So, that means if I take the probability when I give the probability here, the probability will be increasing. The probability of this one is less than or equals to probability of this one, and that is what basically I have written in this statement. So, we have that for a particular n, any particular n, p I j n is less than equals to p I union n equals to 0 to infinity x n equals to j. Now, this statement and this statement are exactly same, because I is given here. So, I am starting from I and union is n. So, that means I will be j in some step. Union is union of x n equals to j, union is over n equals to 0 to n, that basically mean that I will be j in some step. So, ever be in j. So, I will be ever be in j, that is exactly this one. So, these two events are exactly same, one is written in words and another is written in mathematical form. So, we have these two probabilities has to be same, we have written the same thing. Now, come to the next one is again the same thing written in a different form, it is nothing but p I, again this starting from I have written I here, and then x n equals to j for some n greater than equals to 0. So, these three statements, these three things are basically writing of the same thing in different notation. So, I have just written it here to tell you that the same thing can be written in these several ways, and in many scenarios one is helpful rather than the other, that depends on what kind of problem we are trying to solve. So, these three things are same. Now, come to this expression, why this inequality is there? This is because this is coming from this one, this is coming from this one. We know that probability of union of I equals to 1 to infinity is less than or equals to summation probability of I equals to 1 to infinity, that we know. Okay. So, based on that, now I can easily write this one from here, because this one is less than or equals to, if I take a n equals to j as a I set, a n equals to j as a I set. So, this is same as, this is less than equals to n equals to 0 to infinity, probability starting from I x n equals to j, and this is basically p I j n. This probability is basically p I j n. So, we can write that p I j n is less than equals to p I of union n equals to 0 to infinity x n equals to j is less than or equals to summation n equals to 0 to infinity p I j n. Okay. So, first step is true, because I have taken a particular n here, where here we have all the n's. So, x n equals to j is a subset of union of x n equals to j, n runs from 0 to infinity. That is why the first inequality is true, and this inequality is true because of this basic inequality in the probability. Okay? Basic inequality in probability, this inequality is also true. Now, after writing this thing, the equivalence of 1 and 2 can be proved very easily. So, suppose now that the first condition is true. Suppose now that the first condition is true, that is j is accessible from I. So, that means there exists a n such that p I j n is strictly greater than 0. So, that means if I take that particular n here, so this quantity has to be strictly greater than 0. If this quantity is strictly greater than 0, now this ever be in j starting from I, that quantity is even bigger than p I j n. So, this quantity also has to be strictly greater than 0. Okay. So, if I assume 1 is true, we can show that 2 has to be true. Now, when I try to prove the prove that if 2 is true and then 1 is true, so suppose 2 is true, we try to show 1 is true. Okay. Now, 2 is true, that means this probability is strictly greater than 0. This probability is strictly greater than 0, and notice that summation p I j n even bigger than this particular thing. So, this summation p I n has to be greater than 0. So, this shows that summation n equals to 0 to infinity p I j n is strictly greater than 0. Now, that shows that this implies that at least one n is there exists a n greater than equals to 0 such that p I j n is strictly greater than 0. Why? Because if there does not exist any n such that p I n is strictly greater than 0, then this sum has to be 0. Then the sum has to be 0, because if I add 0 up, whatever time does not matter, it will remain 0. Okay? That is why basically p, that sum is strictly greater than 0, that says that at least one of the entry has to be strictly greater than 0, otherwise sum will be equals to 0. Okay? So, that proves the equivalence between 1 and 2. So, basically once I have this particular expression, the proving of the equivalence between 1 and 2 are very simple. Now, we will look into the proof of the equivalence of 1 and 3. So, now we will look into 1 and look into 3, and we will try to prove the equivalence of 1 and 3. To prove this one, first we have to understand this particular expression. So, what is this particular expression? Just recall that P2 can be written as P square. So, what does this mean? This is basically nothing but product of the matrix P into P. Similarly, we have also discussed that Pn is nothing but P to the power n. So, I need to multiply P to the power P in P for n times. I have to multiply P for n times. That is the matter. Okay. So, now we know that when we take the multiplication of two matrices, that basically mean that I have to take the rows of the first matrix and then the column of the second matrix, and I have to take the multiplication of the row times the column, row of the first matrix times the column of the second matrix. Okay. So, if you keep on doing this, then P to the power n basically turns out to be some combination of like this, some combination like this. Okay. And that basically tells that P I j n can be written as summation I1, I2, In minus 1 belongs to the state space, and then I have this expression. This is probability moving starting from I going to I minus I1. starting probability starting from I1 to going to I2 and so on so forth. Finally, probability that starting from n minus 1 going to state j. So, if I take the sum of this, I will get that. So, this one basically coming from the definition of matrix multiplication, and just you write the matrix multiplication for 2, you can also understand that how this is coming. Okay. So, this is actually coming from that, and once I have this expression, now proving that 1 and 3 are very, very simple. How? Because suppose that 1 is true. So, what we try to prove? What we try to prove? Try to show that 3 is true. Okay, that's our job, and now it is easy because see 1 is true, that means j is accessible from I. So, what does this mean? This means there exists a n such that this quantity is strictly greater than 0. Okay, there exists a n such that this quantity is strictly greater than 0. This quantity is strictly greater than 0. So, that means this sum is strictly greater than 0. And this sum is strictly greater than 0, that means that at least one of the entry inside the sum has to be strictly greater than 0. So, that proves the third part. Okay. So, that means that basically shows that summation p I I1, p I1 I2, so on and so forth, p I n minus 1 j is strictly greater than 0, and this implies that at least one p I I1, p I1 I2 and so on and so forth, p I n minus 1 j has to be strictly greater than, at least one of them has to be strictly greater than 0, otherwise this sum will be 0. If all the entries here are 0, then the sum will be 0, but we know that the sum is strictly greater than 0. Okay. Using this we can prove that 1 implies 3. Now we have to prove that 3 implies 1. Okay. So, to do this, so we want to prove now is that suppose 1 is suppose 3 is true, suppose 3 is true, try to show that 1 is true. Okay, that is what basically we try to do. Now, this is true, that means that there exists at least one one set of I1, I2, In minus 1 such that this quantity is greater than 0. So, 1 is true, that means that there exists at least one set of I1 to In minus 1, I1 to In minus 1 such that this quantity is greater than 0. That was the third statement says. Now, if this quantity is greater than 0, that means at least one of the entries here greater than 0. So, summation has to be greater than 0, because this product will be always non-negative, because this is the product of some probabilities and probabilities are non-negative. So, product of the probabilities are also non-negative. So, if one of the product is strictly greater than 0, then the sum has to be strictly greater than 0, and this shows that there exists some n greater than equals to 0 such that this quantity is strictly greater than 0. So, that shows that if 3 is true, 1 is also true. So, that shows that the equivalence between 1 and 3. So, previously we have proved the equivalence between 1 and 2, now we have proved the equivalence between 1 and 3. So, that shows that all these three conditions, 3 statements are equivalent condition. So, that means showing that j is accessible from I is same as showing that second condition, that ever in j, probability that ever in j starting from I, given that starting from I is strictly greater than 0, and which is again equivalent to show that there exists a path from I to j, and this path in this case is through I1 to In minus 1. Okay. Through I1, I2, I3, so on, In minus 1, I can go from I to j. That is basically the idea. Okay. So, with that, let us proceed and let us now see what does this communication mean. So, the definition of the communication basically comes from the definition of the accessibility. And the intuition behind the definition of communication is as follows. See, as I told that maybe the Kolkata is accessible from Guwahati, that means that I can go to Kolkata from Guwahati. Okay. On the other hand, Guwahati is accessible from Kolkata, that means I can go to Guwahati from Kolkata. Okay. Now, because in this particular case that Guwahati and Kolkata, both of them are accessible from the other, that means that these two places communicates between themselves. Okay, that means that these two places communicate between themselves. So that is the essence of the communication, that if I have two states I and j, if I can go from I to j and j to I, that means if I is accessible from j and j is accessible from I, then we say that the two states I and j communicates. Okay. So let us now go by the definition line by line. Two states I and j are said to communicate if I and j are accessible from each other. Okay. So that means from I can go to j, from j I can go to I. So if here I, here j, I can go from I to j, I can go from j to I. Note that that may not be in one step, but maybe in few time step I will go. Some time step I can go from I to j, in some other time step maybe I can go from j to I. Okay. And then using the definition of the accessibility, that in mathematical term I can write that there exists m greater than equals to 0 and n greater than equals to 0, both of them are integer, such that p j I m is greater than 0. So from j I can go to I in m step, from j I can go to I in m step, and from this I can go to j in n step. That basically comes from here. Okay. So there in n step I can go from I to j, in m step I can go to j to m. So that means I can go from I to j, I can go from j to I, and that means they communicates. Okay. They communicates. So some notation, this notation now onwards we will going to use. J is accessible from I, that means I can go from I to j, that we will denote by this arrow notation. And keep in mind, this arrow does not mean that I will go in one step, it basically means that in some step I can go from I to j. Whatever the step, that depends from problem to problem. In some problem maybe I can go in one step, in some problem I can go in multiple step. Just like you can take this example, suppose I want to go to Indore from Guwahati. Now there may not be direct flight to Indore. Okay, there may not be direct flight to Indore, but what I can go is that from Guwahati I can go to Delhi, and from Delhi I will go to Indore. Okay. So in one step in this case I cannot go, I have to take two flights. So one step I may not be able to go, but the things are that they are accessible, because via Delhi I can go. Similarly, from Indore I can come back to Guwahati via Delhi. So maybe in this case again one step I cannot go, but via Delhi I can go. I have to take two steps, but that's okay, I can go, that's it. If whether I can go or not, that is the important here. Okay. Now suppose that tomorrow some direct flight started between Guwahati and Indore, so that means from tomorrow I may go directly from Guwahati to Indore. In one step I can go from Guwahati to Indore. Okay. So it's important in this case, in case of accessibility and communication, the importance is that whether I can go or not. How many steps I need, that is a different issue. We are not care about that in this particular case. Whether I can go or not, that may be in multiple steps, that may be in one step. It does not matter as long as we are concerned about accessibility and communication. Okay. And the communication we will denote by this notation. So you can understand from here that here I to j I have one side arrow, but when the communication there I have two side arrows, that means from I can go to j, from j I can go to I. Okay. So that is basically the essence or intuition behind communication, and this is the definition of the communication here. So let us now proceed. So before proceeding this one, let us again talk about some practical thing. So in our family we have different relationships, like I have my father, mother, grandmother, sisters, brothers, so on and so forth. Okay. So now in some relationships has some special characteristics, whereas some other relationships do not have those characteristics. Just for example, talk about the relationship between myself and my father. So, my father, suppose I am Ayon Ganguly and my father is Malay Ganguly. So, the relationship from A to M is basically father. A to M is basically father. Okay? But the relationship from M to A is basically son. So, that means in this particular case M is father to A. That does not mean that A is also father to A. That is not true. But suppose I am Ayon Ganguly and I have a brother, suppose name is Bhaskar. Okay? I have a brother name is Bhaskar. Now, in this case, this relationship is brother, whereas the opposite relationship is also brother. So, you see that there are two different kind of relationships here. One is that when it is a father relationship, that means M is father to A. That does not mean that A is father to M. In fact, A is not father to M. But A is brother to B. That also implies that B is brother to A. So, we have such thing in practice. Then when I am talking about relationships, some relationships are both sides, the same relationship hold in both sides. In some cases, the same relationship does not hold in both sides, but some other relationship comes on the opposite side. Okay? Like father and son in this case, that if I go from A to M, it is father, but M to A is son, but A to B is brother, B to A is also brother. Okay? So, such kind happened in case of communication also. So, communication I can think as a relationship. The reason is that in this case I am talking about the relationship of two persons. When I am in family, I am talking about the relationship between two persons, relationship between myself and my father, or myself and my brother, myself and my sister, myself and my mother, and so on and so forth, or the relationship between my father and my mother. All those things we can talk about. Okay? But the same kind of things are there in case of the communication also. In case of the communication, we have two states, I and J, and the relation communication is in between. So, that communication I can think as a relationship, as a relation. Okay? So, in family I have two persons, I have a relationship between two persons. In case of the communication of the Markov chain, I have two states and I have a relationship between these two, and the relationship is between nothing but the communication, that from I can go to J and from J I can go to I. Okay? Fine. So, now in case of those such cases, I can talk about some property of that particular communication relation. Okay? I can talk about some properties of the communication relation. That the properties are basically coming from that of our normal life, normal family. First property is called reflexive, and that is that I has a relationship with I. So, myself has a relationship with myself, and what is that? That is the self relationship. So, I has self relationship with I here means myself, I here means basically myself. So, I have self relationships with I, and the other side I has a relationship with I, that is the self relationship. That is basically the first condition, that is called the reflexive, that I has communication with I. And that is true in case of our communication also. I will come back to this one also, why this is true in case of the communication also. First thing from our family perspective. Okay, first things from our family perspective, then we will come back to our communication thing. Symmetry. Symmetry basically mean if I is communicating, if I has relationship with J, then J has the same relationship with I, like brother. So, brother is basically a symmetric relationship. Okay, brother is basically a symmetric relationship because that A is brother to B, B is also brother to A. So, that I has related to J, that imply and implied by J is related to I. Okay. So, that is there, and now talk about the transitive relationship. Transitive relationship says that if I and K are related, then by some relation, and k and j is related by the same relation, then I and j are also related by the same relation. I and k are related by one relation, k and j is related by the same relation, then I and j are related by the same relation. That is true for brother. You see that that is true for brother, but that is not true for father, because suppose I have now a son, maybe I have now a son, maybe called the name of my son maybe start with S, then it is also if it is I have a son now, its name start with S, so its name is this relationship again is father relationship, but of course that does not mean that M is father to S, So this is not symmetric. Father relationship is not symmetric, it is not transitive, but this relationship is transitive also. The brother relationship is transitive also, because if B has another brother called C, then A and C is also brother. A and C are also brother. Okay, so A is brother to B, B is brother to C, then A is brother to C. So the brother relationship is symmetric, transitive, but father relationship is not symmetric, not transitive. So some relationship have some properties, some relationship may not have that property. And for our case, the main idea is that this communication relationship has these three properties. The communication relationship has these three properties, and we can very easily show this thing from the definition of the communication. First, reflexive. Why this reflexive thing is true? Because we know that P I 0 is equals to 1, so it is strictly greater than 0. So there exists some n such that P I in this case basically I take n equals to 0 and P 0 is equals to 1. So this reflexivity is whole true, that I is communicating with I and I is communicating with I on the other hand also. So this is true. Now think about this symmetry. Symmetry tells that I related to j, I is communicating with j, that means there exists some n such that this quantity is greater than 0, some m such that this quantity is also greater than 0. Now j is communicating to I, that basically means because this is greater than 0 and this is greater than 0, this part is also true. So the proof of first 1 and 2 is very trivial, but the proof of the last one is not that trivial. Let us discuss now the proof of the transitivity. So the proof of the transitivity goes like that. First, what is it saying? It is I is communicating with j. So that means there exists some n such that this quantity is strictly greater than 0, and there exists some m such that this quantity is strictly greater than 0. Then k is communicating to j. So that means there exists some, maybe I call L, such that j is strictly greater than 0, and there exists some maybe q such that this quantity is greater than 0. Okay, there exists some n such that this quantity is greater than 0, m such that this quantity is greater than 0. This one is true because of I is communicating with j, and because k is communicating with j, that's why there exists L and Q such that both the quantities are strictly greater than 0. Now think of this I to k. So first notice that from I to j in n plus L, so what I have done is that this n I have taken, this L I have taken. So using the Chapman-Kolmogorov equation, I can write this one as P I1 P I1 j, and this is in n step, this is in L step, and I take the summation over I1 belongs to S. Okay, this is the using Chapman-Kolmogorov equation, this equality holds true. Now see that this n, because this n1 is, when I am taking this I1 belongs to S, so I1 also take the value k. So I can write this quantity is greater than or equals to P I k in n step, P k j in L step. Okay. So I have taken a particular value of I1 belongs to S, and k is a member of S, in member of state space. So that's why I have taken a particular value of I1. So that means basically one term I have kept here because all of them are probability. So this one particular term will be less than or equals. So this quantity is greater than or equals to this quantity. Now both of them are strictly greater than 0 because one here, another is here. So this quantity is strictly greater than 0. So that shows that from I to j I can go in n plus L steps. So that means that j is accessible from I. That means that j is accessible from I. Similarly, now we can show that I is accessible from j, just writing that try to find out that p ji in m plus q step. The same manner I will do and we can show that this quantity is strictly greater than 0, and that shows that I is accessible from there. So j is accessible from I is accessible from there, that shows that I and j communicates. Okay. So that is basically three properties that are satisfied by communication relationships, and if these three properties are satisfied by some relationship, then that relationship actually partitions the state space. Like our family, see, talk about the brother relationship. Okay, in case of the brother relationship, you see that the my brothers, they are one class of my family, one set of my family. If you think of all of your uncles including your father, so that is another class of brothers, that is another subset of the family. Okay, and you notice one very important thing here, that all the members in the class where all my brothers belongs, and all the members in the class where all my uncles and father belong, these two sets are disjoint sets. There is no common member which belongs to both the sets. Okay, so that means that my family is partitioned by this relationship, and the same thing happens in this case also. And what we can basically do, we can tell here is that if I have this state space, set is given by that, then the any equivalence relation actually partition the state space into several groups, and where the member of each group, each class, that all the members here communicate among themselves. All member communicates. Okay, all members here communicates. Similarly, all member here communicates, all member here communicates, all member here communicates. But a member from here may not communicate with the member, will not communicate with a member of the other class. Okay, a member of one class will not communicate with another member of the other class. But the thing is that, see, that I can go from here to here, that's not a problem, but I cannot come back from here to here. That's the thing. Okay, so that is basically the idea of the communication, and that says that communication is an equivalence relation, and any equivalence relation actually partitions the set. In this case, the communication, in this case, that communication relationship partitions our state space, and it partitions the state space into communicating classes, that each parts are called the communicating classes. This is one communicating class, this is another communicating class, this is another communicating class, this is another communicating class, and this is another communicating class. We will discuss all this concept using some examples also. We will see some examples in the next slide. Before going into that example, let us see some more definitions which are quite meaningful in this case. The first definition is about the closed communicating class. So a communicating class C is said to be closed if this happens. What does this mean? Notice that this C is a class, C is a communicating class, okay, and I belongs to here, and I can go from I to j, I to some j I can go. Okay, j is another state, I can go from I to j, and this implies that j belongs to C, so that j has to be in C, so j is somewhere here. Okay, so that basically mean closed. So if I can go from I to j, if I belongs to a communicating class, then j has to belongs to the same communicating class, then C is called, then that communicating class is called closed. Okay, and that basically mean that if I have a closed communicating class, and if I am already in that class, I cannot go out of the class. Okay. If I have a communicating class C, and if I am already in the class C, then I cannot go outside that closed class. That is basically the idea of the communicating class. Now, talk about the observing state or observing class. So, suppose I is a state which is a observing, which is called observing state. If I consider this class, this is the singleton set, this class, this is a closed class. Okay. If I as a singleton set is a closed class, then we say that it is a observing class. What does this mean? That means once I am in I cannot move out from I will be I forever. So, that kind of classes is called the communicating class, observing class and observing state. So, this kind of state we have seen earlier. Just recall that the examples we have talked about in the previous lecture. So, in that lecture we have talked about some classes that once I am in that class, I will be there forever. Like in the last example, when we talk about the class 4, which basically class 3, which basically means that the sequence of 3 consecutive head has already occurred. So, once I am in that class, I cannot go out of this class. So, that kind of class is called the observing class. So, we will see some more example as we proceed. And finally, irreducible Markov chain, that basically mean that your state space S is a closed communicating class, Okay. So, a Markov chain is said to be irreducible if all states communicate with each other. That means a single communicating closed class is there, Okay. So, if all the states communicate among themselves in a Markov chain, then that Markov chain is called irreducible Markov chain. And for that simply says that for a irreducible Markov chain, starting from any state, I can go to any other state. Okay, there is a positive probability to go to any other state starting from any other state. Okay, that is basically the irreducibility mean. Okay, now let us see some examples. So, let us start with this example. Okay, before starting this example, see that we have pointed out that if I am given with the initial distribution and the one step transition probability matrix of some Markov chain, the Markov chains, all the probabilistic characteristics of the Markov chains are specified. Okay. So, in this case, of course, I have not given the initial distribution, but I have given only the one step transition probability matrix. And the interesting thing here is that that of course do not specify all the probabilistic characteristics of a Markov chain, but given the one step transition probability matrix, I can check whether the classes communicates, classes accessibility, closed class, all those things we can actually see. To do this one, the easiest way to do is that to draw the graph. What kind of graph? Let us discuss that. So, in this case, I have 3 states 0, 1, 2. Suppose these are the states. Okay. Now, you see that in one step there is a positive probability for going from 0 to 0. Okay. In one step there is a positive probability from going to 0 to 0. So, I just write the path like this. From 0 I can go to 0 with positive probability. Similarly, in one step I can go from 0 to 1. So, with positive probability I can go from 0 to 1. So, I just write like this. So, this way I will add all the edges. So, it is kind of a graph we are plotting, we are writing, and here you can see that 0, 1 and 2 are nodes, and these are the edges, and edges means there is a positive probability of going from one node to the another node. Okay. So, that means that I have in this case basically from 0 to 0 with positive probability I can go. So, this edge comes from 0 to 1 with positive probability I can go. So, this edge come, but there will be no direct edge between 0 and 2 because in one step I cannot go. Here I am writing everything for one step thing. Okay. Next, from 1 I can go to 0 with positive probability, 1 I can go to 1 with positive probability, 1 I can go to 2 with positive probability. So, this arrow comes here, this loop comes here, as well as this arrow comes here. Similarly, from 2 I can go to 2, from 2 I can go to 2 with positive probability in one step, and from 2 I can go to 1 with positive probability in one step. Okay, I can go in one step with positive probability. So, this graph is basically nothing but whenever I have a directed edge, that means I can move from one to another state in one step. Whenever I do not have I mean there is a positive probability of moving from one node to another node in one step. Whenever there is no edge or no directed edge between two nodes, that means from that particular node I cannot move to another particular node in one step. So, in this case, see that I do not have any edge between 0 and 2, that basically signifies that in one step I cannot go from 0 to 2, but there is a directed edge between 0 to 1. So, that means that in one step there is a positive probability for going 0 to 1. Okay. Now, once I draw this one, that checking that what are the classes communicates, all those things is very, very simple. First, think about state 0 and 1. From 0 I can go to 1, there is no problem, in one step I can go. Okay. From 1 also I can go to 0. So, clearly because in one step actually I can go in one step with positive probability. So, that means that state 0 and state 1, they communicate among themselves. In one step I can go from 0 to 1, there is a positive probability of going from 0 to 1. Similarly, in one step there is a positive probability to go to 0 from 1, okay, and 1 to 0, both sides are possible. Similarly, so that means that 0 and 1 are actually communicates. Similarly, 1 and 2 also communicates, because in one step there is a positive probability of going to 2 from 1. Similarly, there is a positive probability of going to 1 from 2 in one step. So, that means 1 and 2 also communicates among themselves. What about 0 and 1? In this case, of course, I cannot go in one step, but you see that from 0 in one step there is a positive probability of going to 1, and from 1 there is a positive probability of going to 2. So, that means 2 is accessible from 1, 2 is accessible from 0. Okay, 2 is accessible from 0, because from 0 I can go to 1 with positive probability in one step, and from 1 I can go to 2 with positive probability in one step, and that means from 0 I can go to 2. Of course, in this case in one step I cannot go, but in 2 step I may be able to go. Similarly, from 2 I can go to 1, then from 1 I can go to 2, 0. So, these two classes also communicates, these two states also communicates. So, in this case I have these 3 states, all the 3 states communicates, and so this is one class in this case, just one class exists in this case, one communicating class exists in this case, and this class has to be closed, because this is the whole the state space, this is the whole state space, and because all the states in this case communicate among themselves, the Markov chain is a irreducible Markov chain, the corresponding Markov chain is a irreducible Markov chain. Let us proceed to next example. Again a one step transition probability matrix is given, and again if you see, we can draw the diagram, the graph like this, and again the interpretation are same, that if there is a directed edge I can go, there is a positive probability of going from one to another in a one step. So, I have this. Now I can see that 0 and 1 communicates. So, clearly 0 and 1 communicates. Okay. What about 0 and 2? See that from 0 I cannot go to 2, because there is no path. From 0 I cannot go directly to 2, from 0 I cannot from 0 I can go to 1, but from 1 I cannot go to 2. So, these two communicates among themselves. Okay. So, these two makes one class, one communicating class. Now, talk about 2. From 2 I can go to 3, fine, but 3 I cannot come back to 2, because 3 basically from 3 I can only go to 3. So, of course, 3 is accessible from 2, but 2 is 2 is not accessible from 2. Okay, but 2 is not accessible from 3. So, that means these two classes do not communicate, and that means that 2 is separately one communicating class and 3 is separately another communicating class. So, we have this particular thing, 0 1 is one communicating class, 2 is along one communicating class, 3 is along another communicating class. 0 1, this comma will not be here. 0 1 is basically closed. 0 1 is basically closed. That means once you in 0, you cannot come out of this class. Similarly, once you are in 1, you cannot come out of this class. From 0 you can only go to 1, 1 you can only go to 0. So you will be always here. You will be always here. Similarly, 3 is closed, because once you are in 3, you can only remain in 3, because only one path, one directed path is there, one directed edge is there. So you will be in 3. So these 0, 1 and 3 are closed, plus 2 is not closed. The reason is that from 2 I can go to 1. So from the, starting from 2 I can go out of this particular class, out of this particular communicating class. So that's why 2 is not closed. And of course this is not irreducible, because I have 3 communicating classes in this particular Markov chain. Similarly, let us talk about this. It is little bit bigger, but the things are almost same. You have this particular diagram, and now in this case it is easy to see. Again, we have 3 communicating classes, that 0, 1 and 2. These actually make one communicating classes. 3 alone makes one communicating classes, and these 2 makes one communicating classes. And in this case 4, 5 is closed, this one is closed, the others are not closed. The reason being that from if I start with this one, suppose I am in 0, from 0 I can go to 1 with positive probability, from 1 I can go to 2 with positive probability, and from 2 I can go to 4, I can go to 3 with positive probability, and when I go that I am out of this class. So clearly the first class is not closed. Similarly, this class is also not closed, because from 3 there is a positive probability of going to 3, going to 4, that means I can go out of this communicating class. So that's why this is not also closed, and there is no question of irreducibility, because I have multiple communicating classes. Recall that irreducibility meaning that I have only one communicating classes, and in this case I have multiple communicating classes. So clearly this is not irreducible Markov chain. Okay. So these are some examples. So today's lecture, just recall, we have learned what is accessibility, what is communication, and then we have pointed out that communication satisfies three conditions: reflexibility, symmetry and transitivity. And that means that the communication can be seen as a relation, and that relation partitions the state space, and each partitions are called communicating classes. And then through some examples we have shown that how using diagram, using graph, we can easily find out the communicating classes, closed classes of a Markov chain from one step transition probability matrix. With that I stop. Thank you for listening.